So whenever we define a random variable, so random variable is a function from a sample space to R. It is not only the function, it is a measurable function. So you know that. So random x is a measurable function from S to R. So any S belongs to S, so this will be a real number. And not only that, if you consider a Borel set, so x inverse of the Borel set will be in the sigma field of this sample space. We consider the class of subset of S, that is a sigma field. So then only it will be a measurable function. Now if you consider a function, suppose, so x is basically, suppose it is a sample space S, and here this is set of real number, and then we consider another function here. Suppose g, this is R to R, one function. So let us consider one function g R to R. So any real number here, it will be some value here. Suppose here x is here, so then it will be some g of x will be some value here. So this is a function from R to R, any function. Then if we consider, so there is always a function. Suppose for a particular value of x, let us assume that this is going to x. Let us, it may be any value of here, but here assuming that, so a is going to x under this random variable x. So this is nothing but x is nothing but x of s. So now what will be g of x of s? G of x of s will be nothing but g of x. So this is again a function. So if you consider this composite function g composite x, if you consider, so that is defined by g composite x is nothing but, this is again function from S to R. So any value g in any value s in R, again it will be g of x of s. This is again a real number R. So then this function, if it is measurable, suppose if you consider g is such a function that this composite function, it will be a measurable function. It may be, so basically if you consider a continuous function, then g will be a measurable function. So then this composite function will be again a measurable function. So then this is known as this will be another random variable. So in a short notation, this g composite s, we say y is equal to g of x. So basically y is a random variable, that means measurable function y s to R, defined by y of s is nothing but g of x of s. So this is another random variable. Now this kind of concept we have used already to find expected values of, but using the probability distribution function of x. But if you want to know, we are interested that we want to find expected values of y, variance of y with respect to probability distribution or probability mass function in case of discrete, probability density function in case of continuous, of y only. So then we need to find that. So then how to find that? So we want to know, suppose let x be a random variable with the cumulative distribution function CDF fxx. So that is known to us, and g R to R, it is a measurable function. Let be a measurable function. So we can consider some function such that this function, then what will be the distribution? What is the cumulative distribution function CDF of y? This is gx. So how we can find the cumulative distribution function of y? That is our interest here. So the CDF of y, the cumulative distribution function. So we are writing as a abbreviation. The cumulative distribution function of y is given by, so f of y. This is probability that y less than equal to small y. So how we can find that? That probability that g of x less than equal to y. So we can write this probability that x belongs to d of small y. What is dy? So dy is nothing but dy is all this set belongs to sample space S such that g of x of S actually less than equal to small y. So, this is the set. So, that means that we are interested to know. So, this is the dy. So, we can just directly write instead of like this probability of dy you can write. So, in a different, so it is just a notation only to understand, or we can say just directly probability of d of y. So, this is the actually subset of the sample space. So, this is the probability of dy, or some here in this slide you can see that it is just notational, it is right, x belongs to dy. Now, okay, so this is the things, this is the, now since we do not know explicitly what will be the distribution. So, basically we can find this probability, but in a particular cases how we can find. So, let us discuss some of the example. So, one example let us consider, suppose we are tossing a coin. So, tossing a coin, we consider the sample space S is either head or tail. So, this is head or this is tail. So, then it is mapping up to we are considering that this random variable x of 1 is x of head is 1 and x of tail is 0. Now, if we consider gx is this function R2R. So, now we know the probability mass function, probability distribution function, but if it is a discrete random variable, so we represent this random variable by a probability mass function, it is easy. So, probability of x is equal to 1, suppose this is some p belongs to some 0 1, and probability of x is equal to 0 will be 1 minus p. So, this is the probability mass function. Now, we are interested one transformation. Let us consider this transformation g R2R defined by g of x is equal to, let us consider very simple transformation instead of going very complicated, x plus 2 suppose. Okay, this is the one transformation. So, now now this is the transformation. Let us consider this random variable. Let us consider the random variable y is equal to x plus 2. So, this is g of x, this is equal to x plus 2. So, what will be the probability mass function of y? So, let us find out the probability mass function of y. So, the probability mass function of y is given by, so first of all we have to find what will be the range of y. So, range of y, it is, so what are the values it can take. So, now there is S here, head and tail, and then this real number here. So, head goes to by under x of head, it is going to x of head goes to some value 1, and x of tail, this goes to some value 0, some point. Now, under gx, so gx is equal to, g is a function from R to R. So, g of x is equal to x plus 2. So, if you consider this 1, it is going actually, this is going, okay, whatever. So, yeah, so it is actually x g of 1, this is nothing but 1 plus 2, 3, and g of 2, this is g of 1, and g of 2 is 2 plus 2, 4. So, this is equal to g of 2. So, hence y of head, it is nothing but so y of head is, this is the random variable, the composite random variable, this is going to this value and tail goes to this value. So, y of head is nothing but x of g of x of head. So, g of 1, this is 3, and y of tail is g of x of tail, this is g of, so this is 0 actually, so that is a mistake, x of x of tail is 0. So, g of 0 is 2, g of 0, this is g of 0. So, g of 0, this is 2. So, now the random variable, we know that probability of head is p. So, probability of x is equal to 1, this is p. This is same as now, because x equal to 1 means that tail occur. So, this is same as probably that y is equal to basically y of head occur means x of is equal to 1 means head occur, this is probability of p. So, in this case of random variable y means y is equal to, it will be 3. So, similarly x is equal to 0, so this is p. So, 1 minus p, that tail occur. So, it is equal to probability that y is equal to 2. So, now this probability mass function of y changed. So, then we can usually you can find this their cumulative distribution function also everything. So, just for simplicity we just try to understand that how this if you consider a transformation, their probability mass function can be found. Now, in general cases we will discuss, it is hopefully you have understood that how transformation of random variable, how we can find their probability mass function. So, here it is very simple example. Now, one by one we will discuss little more general cases. So, for example, for continuous cases we need to do this kind of integration. So, how we will do that? Let us discuss some of the examples for general cases. Let x be a random variable with cumulative distribution function f(x). Find the cumulative distribution function of y is equal to x plus a for some a belongs to real number. So, it is just as before what we discussed, this kind of. But it is more general case, not the just the head tail example. Let x be a random variable with cumulative distribution function, suppose some f(x), it is known, and g r to r be a function defined by g of x is equal to x plus a for some. So, this is a fixed value, some a belongs to some real number, maybe 2 or 3 or 0, any value. If it is a is 0, it is nothing but the identity function gx is equal to x only, no change. So, same random variable, we need not to find any different distribution functions, with same distribution function it will work, but for any other transformation, non-zero transformation, we need to find the cumulative distribution function. The cumulative distribution function, okay, the CDF, cumulative distribution function of y is equal to gx. So, this is the transformation random variable. So, what is that? X plus a for some particular values of y, a belongs to real number. CDF, the cumulative distribution function of y is equal to gx is given by f of y, this is equal to probability that y less than equal to y. So, how we can find this probability? So, because y is gx, so probability that this is gx less than equal to y. So, note that y is some real number, y is belongs to some real number. Now, we have to find the probability. So, what is these things? So, gx is nothing but probability that x plus a less than equal to y. So, then we can write is this probability same as x less than equal to y minus a. Now, what is this? Because we know the cumulative distribution function of f(x), since f(x) is CDF of x. So, what does it means? f(x) is nothing but probability that x less than equal to x. So, x is any real number. So, that means f(x) of, if you put this real number y minus a, it is nothing but probability that x less than equal to y minus a. So, this is nothing but, so x less than equal to y minus a is nothing but, if we know this f(x) we know, so we can write f(x) of y minus a. So, that is why for any this some particular values of y, we know this function, so then we can find the cumulative distribution function of y. So, this is just general case, we can have some particular example. So let x be an exponential random variable with parameter 1. Find the probability density function of y is equal to 3x plus 5. So how we will do that? So this is just, see that earlier case it is just a addition. So now here we can take some multiplication also, 3x plus 5, but similarly we will do that. So but here they asked for, in this question it is asked for probability density function. So because it is a continuous case, we but here it is easy to find the cumulative distribution function. Now let us do that. So let x be an exponential random variable with parameter 1. Let x be a, so let x be an exponential random variable with parameter 1. Find the probability density function of 3x plus, find the probability density function of y is equal to 3x plus 5. So here we consider this gx is nothing but 3x plus 5. So since the probability density function of x which is as exponential random variable with parameter 1 is of x is given by, so f of x is so because exponential random variable lambda e to the power minus lambda is 1 here, so e to the power of minus x whenever x is greater than 0, less than infinity, 0 otherwise. Now as we know here whenever we found, so you can see that for cumulative distribution function it is easy to find. For probability density function we do not know how to find that. Probability density function we have to take the derivative of this cumulative distribution function. So now here they asked for probability density function. First we will find the cumulative distribution function. So what is this cumulative function? The cumulative distribution function of x is given by, so this is f of x, this is probably that x less than equal to x. So we just you can recall that this will be 0 if x is less than 0, greater than minus infinity, because no density here, and then you have to integrate 0 to x, then this is your density function is e to the power of minus t dt whenever x is any value greater than 0. So we can write less than equal to 0, less than infinity. So then if you compute these things, so this is nothing but 0, this is x greater than, so this is the density we are integrating probably x less than equal to x. So minus into x, but minus into 0 it is 0. So 0 plus 0 into x, 0 to x e to the power minus t dt. So because x we are using this variable, so that is why we change this variable to t only. So it is the density function here e to the power of minus t. So then x is minus infinity less than equal to 0, then this is 0. Now if we do this integration, this is nothing but minus of, so what will be this integration? This will be minus of t, and this is limit is 0 to x. So now at x e to the power minus x, minus of e to the power minus x, minus of then e to the power of, so another minus, so plus t is 0, then this is 1. So this is 1 minus e to the power of minus x if x is greater than 0, less than infinity. So this is the cumulative distribution function. So once we have found the cumulative distribution function, then we will try to use this concept. So let gx is this transformation, let us consider this transformation, gx is equal to 3x plus 5, this transformation it is given here. So we can see that gx is equal to 3x plus 5. So now y is gx, this is equal to 3x plus 5. So then the CDF cumulative distribution function of y is given by, so cumulative distribution function of y is given by so f of yi. So by definition this is equal to probability that y less than equal to y. So this is probability that gx less than equal to y. So because y is nothing but gx, so probability that gx less than equal to y, which is probability that gx is 3x plus 5 less than equal to y. So this is gx, gx is 3x plus 5 less than equal to y, which is equal to probability that, now we just, because this probability is same as if we subtract it minus 5 both side, again also it is same as if you divide, because 3 is positive number, so the inequality does not change. So all those values satisfies this relation, those values it will be satisfies this relation also, y minus 5 by 3. So y minus 5 by 3. Now what is these things? So you know that f of x, any value evaluated at x is nothing but probability x less than equal to x. Now if you put x, so hence probability that x less than equal to, if you put y minus 5 by 3, it is nothing but f of x y minus 5 by 3. So this is f of x y minus 5 by 3. So this f of x, we know that this f of x, it is given here. So this is 0 if x is less than equal to 0, it will be 1 minus e to the power of minus x if 0 greater than 0 less than infinity. So that we will write here. So this will be is equal to 0 if this value y minus 5 by 3 less than equal to 0 greater than minus infinity, and this is equal to y minus 5 by 3, this is equal to 1 minus e to the power of minus x, 1 minus e to the power of minus y minus 5 by 3 if y e to the power minus x, if this value is greater than 0 less than infinity. So now we can simplify these things, because this relationship we can simplify a little bit. We can multiply both side 3 and add by 5. So this is equal to, this will be equal to 0 if y is, it will be minus greater than minus infinity less than equal to 5. This will be 1 minus e to the power of minus y minus 5 by 3 if actually if y is greater than 5, y is greater than 5 less than infinity. So this is the cumulative distribution function of y. So here using this x is known, so we taking the transformation, then but it is asked that in this question you can see that it is asked that x is an exponential random variable with parameter 1, find the probability density function of y is equal to 3x plus 5. So we have to find the probability density function. So now we found the probability cumulative distribution function. So let us write down this cumulative distribution function. The CDF, cumulative distribution function of y, is given by f of y. This is what we found, 0 if y is greater than minus infinity less than equal to 5, 1 minus e to the power of minus y minus 5 by 3 if y is greater than 5 less than infinity. So now how to find the probability density function? Because it is a continuous random variable, the probability density function will be found by differentiating this cumulative distribution function. So the hence the probability density function of y is given by, so f of y, this is differentiation with respect to f of y. So this is whenever it is 0, this is 0 if y greater than minus infinity less than equal to 5, and then if you differentiate it, so this minus, so this is 1 by 3 e to the power of minus y minus 5 by 3, 1 minus it will be adjusted here, so that is why this will be become plus. So if y is greater than 5 less than infinity. So this is the probability density function of the y. So this is the way of finding. So here you note that if x is continuous random variable, so we want to find the PDF. So probability density function of x is fxx. Now if you take the transformation y is equal to gx, for finding this PDF we have to convert to first f of x, then you have to find the convert first using this transformation gx, you have to find the cumulative distribution function, then you take the derivative to find the probability density function. So, this is the way we have done. So, this is a little complicated process. So, if we could have any method that we can directly, suppose probability density function of x is known, and if we can find directly the probability density function of y, then it could be very helpful, because we need not to go, because most of the time we are interested about probability density function in case of continuous random variable. So, we need not to, because density function we known of x, you need not to find the cumulative distribution function for the sake of for the transformation of finding the probability density function of y equal to gx. So, we just directly find it. So, we will discuss on, let us see that any other example. So, let us first let us do this example, and then we will discuss how we can utilize this concept. So, let us consider this random variable x be a random variable with probability density function of x. So, let us consider this example, let x be a random variable with probability density function between 0 to 1 it is 2x, 0 otherwise. Find the probability density function. So, here also you see that density function is given, we have to find the probability density function. But we know the method here using the transformation of random variable, we have to first find the only cumulative distribution function we have to use. So, let us do that. Let x be a continuous random variable with the probability density function given by f of x is equal to 2x whenever x is between 0 and 1, 0 otherwise. Find the probability density function of y is equal to 3x plus 1 is equal to 3x plus 1. So, now we will use this method, how first we have to find the, so cumulative distribution function. The cumulative distribution function of x is given by, so let us find out f of x. So, f of x is nothing but probability that x less than equal to x, because the density known we can find the cumulative distribution function. So, how, because it is 0 to 1, so this will be 0 if x is less than equal to 0 greater than minus infinity, because there is no density. But if x is between 0 to 1, x is greater than 0 less than 1, so it will be 0 to x fxt dt, fxt is nothing but 2t dt, and then after 1 it will be 1 actually. This is the, we know that this is the properties, or we can write here 1 same actually less than infinity, because you can see that 0 to 1 if you put, then this will be 1. Now, if you simplify this, this is nothing but 0 if x is less than equal to 0 greater than minus infinity, it is t square by 2, t 2 cancel, t square. So, this is x square if x is greater than 0 less than equal to 1, and this will be is equal to 1. So, if x is greater than 1 less than infinity. So, this is the cumulative distribution function. Now, from cumulative distribution function we will find the cumulative distribution function of y. The cumulative distribution function of y, this is equal to, here we consider this gx is equal to 3x plus 1. So, this is the 3x plus 1 is given by f of y, this is probability that y less than equal to y. So, y is equal to gx is probability 3x plus 1 less than equal to small y. So, which is equal to x. So, see that y is equal to gx, so that is why we put y is equal to 3x plus 1 less than equal to y. So now this similarly we will write that 3x, if you subtract it, this is equal to inequality is same as y. So now if you divide by 3, x less than equal to y minus 1 by 3. Now this is same as earlier we discussed, y minus 1 by fx of y minus 1 by 3, because fxx is defined by probability x less than equal to small x. If you put x, small x is y minus 1 by 3, then fx of y minus 1 by 3. Now fx of x is now the definition is this. We will write that this will be equal to 0 if y minus 1 by 3 will be less than 0, greater than minus infinitive, less than equal to 0, and it will be is equal to x square. That means this is y minus 1 by 3 whole square, y minus 1 by 3 whole square if y minus 1 by 3 greater than 0, less than equal to 1, and this is equal to 1 if y minus 1 by 3 less than 1, less than infinity, greater than 1, less than infinity. So note that it is coming from here. I just putting, I am just using it, x is y minus 1 by 3, we are putting it. So now just simplify this. So by simplification it is 0. Now this simplification actually it will be y will be same as minus infinity, y is less than equal to 1, and this is y minus 1 by 3 whole square. So if y is greater than 3, oh it will be 3 actually, sorry, no this is okay, a minute, yeah, so sorry. So it is 0, then I add 1. So this is y is greater than 1, less than equal to, if you multiply by 3 first, then add 1, 4 actually. So this is equivalent to like you multiply by 3 and then add 1. So then it will be 1 if you multiply by 3. So y greater than 4 less than infinity. So it will not change, infinity same as, because multiply with infinitive plus something infinitive again. So if this, so now y minus 1 by 3 whole square, this is 1. So now we have to find the probability density function of y. So this is the CDF. So we finally what we found, this is the cumulative distribution function, but it is asked that you have to find first, we have to find the probability density function of y is equal to 3x plus 1. So what will be that value? So how we can find that? So now we will take the differentiation with respect to y. So the probability density function of y is given by f of y. So this is differentiation with respect to y, f of y. This is equal to, since it is 0, whenever it is y is less than 1, this is 0. So that we will utilize it. So y is less than equal to 1, greater than minus infinity, because it is 0. So that is why this will be 0. And now if it is between 1 and 4, then this is y minus 1 by 3 whole square. So this is 1 by 9. So then this is 1 by 9 into then y minus 1 whole square derivative, it will be 2 into y minus 1. So this will be 2 into y minus 1, 2 into y minus 1. So 2 by 9 into y minus 1 if y between greater than 1, less than is equal to 4. And what about okay, so then let us see that y minus whole square. So 2 into y minus 1, then derivative of y minus 1 is same. So 1 by 2, 1 by 3, 9. So 9, 2 into 1 minus y. So this is fine, it seems like. And then next we have to find, so then what is at 4, this value will be 4 minus 1. 3, 3 into 2, 6, 6 by 9. So, at whenever now for y greater than equal to 4 less than infinitive. So, it is, yeah, it is less than equal to greater than 4 less than infinitive. So, since it is a constant, if you take the derivative, this value will be 0. So, for simplifying, we can write that it is 2 by 9 y minus 1 if y between 1 and 4, 1 and 4. So, it is a continuous random variable, you can equal or not equal, just a strictly less than you can write, or it is 0 for we are combining both the case. For any other cases this value will be 0. So, just I was checking that whether this all calculations are correct or not, because if you do the integration 1 to 4, so then this should match, like 1 to 4 integration, this should be equal to 1. So, then this is cancelled, then this is 4 minus 1, yeah, so 1 minus 1 0, 3 square 9 by 9. So, it seems it is correct. So, you can check that this is a probability density function. But here also what we did, we know the cumulative distribution function, we want to find x and we want to go from PDF to PDF, but we know the PDF fxx. So, we know PDF probability density function, we find CDF of x. So, then this is PDF of x, we know we find CDF of x, then next we find CDF of y using the concept, and then by differentiation we find the probability density function of y. So, this is this process. So, if you have any method or theorem or some result, so that directly we can find, then we can avoid these steps. So, next we will discuss that one theorem, some important theorem. So, using that theorem we can just directly, if you know the probability density function of x, we can find the probability density function of y. So, why we did, because we know this theorem, but if you use at the beginning, if you use, then you will not understand what is actually transformation of random variable, actually how this probability it is changing, and how this it is actually, this method is the general method. So, this method what we are going to discuss, this may not be applicable for all the cases. So, some of the particular cases it may be useful. So, that we will discuss in the now in the next we are going to discuss.